All right, let's talk about a tech shift that's so fundamental, people are comparing it to the dawn of the space age. But, this isn't about shooting rockets to the stars. It's about diving deep, harnessing the totally bizarre but incredibly powerful rules of the universe at the tiniest scale imaginable. We're talking about America's massive push into quantum technology, and this is what the state of play looks like right now in 2025.
Yeah, this quote just nails it. For so many years, quantum computing felt like something straight out of science fiction, right? Well, not anymore. Now it's a full-blown national priority. We're talking about an organized, super well-funded, and incredibly ambitious movement that is gaining some serious momentum. So that really brings us to the core question, doesn't it? What is America's quantum master plan? What's the real driver behind this incredible investment of money, of talent, of political will? Well, it turns out it's not just one thing. It's a really strategic vision for the future.
When you really boil it down, America's quantum ambition is built on these three massive pillars. First, securing a decisive national security advantage. Second, driving future economic growth. And third, cementing its role as the world's leader in fundamental science. It's a total triple threat.
And look, this isn't just a bunch of talk. It's backed by some serious federal muscle. You've got the reauthorized National Quantum Initiative Act acting as the engine here. And agencies like the Department of Energy and DARPA are just pouring fuel on the fire. We're seeing this coast-to-coast construction boom of specialized infrastructure. I'm talking deep labs, materials foundries, all designed for one thing, to accelerate discovery.
And if you want to understand the scale of this collaboration, just look at this number. Over 400 members in the Quantum Economic Development Consortium, or QEDC. Think about that. This isn't just a handful of university labs tinkering away. No, this is a vast ecosystem connecting national labs, agile startups, policy experts, and all the big tech players. Literally everyone is at the table. And this quote, this one really reveals a critical mindset. See, the ultimate goal isn't just to build a better quantum computer than everyone else. It's way bigger. It's to define the entire field. It's about setting the standards, writing the protocols, and creating the foundational technologies that the rest of the world is going to build upon. So who are the power players actually making all this happen? Well, this entire movement really depends on this unique collaboration, this symbiotic dance between academia, private industry, and the government. Each one is playing a critical and very distinct role. And here's kind of how all those pieces fit together. You've got these academic powerhouses, right? MIT, the Chicago Quantum Exchange, they're the ones pushing the absolute frontiers of theory. Then you have big tech, think IBM, Google, Microsoft. They come in and build the cloud platforms to make this stuff actually usable. And then you have these nimble startups like IonQ and PsiQuantum, who are just laser-focused on one thing, delivering practical results in highly specialized hardware. And you know what ties it all together? It's this incredible convergence. For the very first time, the deep, patient work of fundamental science is meeting the fast, decisive world of venture capital. Investors aren't just curious spectators anymore. Oh no, they are fully committed, funding spin-offs, and fueling this incredibly rapid cycle of innovation. But of course, it's not all smooth sailing. I mean, let's be real. The path forward is incredibly complex, kind of like a quantum labyrinth filled with immense technical and logistical challenges. So despite all this incredible momentum, we have to be realistic about the hurdles that are still out there. Okay, before we even list the hurdles, we have to get our heads around this one term, fault tolerance. So qubits, the fundamental units of quantum information, are just incredibly fragile. They're super prone to errors. Fault tolerance is the absolutely critical ability to correct those errors on the fly. Without it, a big quantum computer is basically useless for solving real problems. It is the number one goal, the holy grail. Okay, with that in mind, 4 major hurdles really stand out. First up, error correction. Today's machines are what we call noisy, and true fault tolerance, well, it's still a wish list item. Second, there's platform chaos. There's no single clear winner yet between all the different technologies like trapped ions or photonics or superconductors. Third, the talent gap. There is a serious shortage of skilled experts. And finally, the geopolitical heat. This is a global race, and nations like China are advancing really quickly. But even with those challenges, practical applications are starting to come into sharp focus. So let's look ahead. Where is this technology going to make its first real-world impact in the very near future? So what can we expect to see? Well, this year, quantum as a service is set to go prime time. What that means is accessing powerful quantum computers through the cloud is becoming a serious tool for industries like finance and drug discovery. By 2026, we should expect to see defense applications rolling out, things like quantum secure networks and ultra precise sensors. And then looking beyond that, those hybrid AI quantum models are going to move from the lab into practical, everyday use. And this all brings us back to that core strategic goal we talked about. By leading in these early applications and pushing the science forward, the U.S. aims to be in the driver's seat when the global rules for this technology are actually written. It's a concept some people call diplomacy by standard setting. Basically, if you lead the tech, you get to write the rulebook. Ultimately, it really all comes down to this simple idea. The era of just dreaming about quantum's potential, that's over. Success now rests on execution, on the steady, really difficult work of building the hardware, writing the software, and training the people to make it all a reality. And so that leaves us with this final, really powerful question. If the United States can navigate all these technical challenges, if it can cultivate its talent and maintain this incredible collaborative momentum, we may not just be looking at the quantum decade. We could be witnessing the very beginning of an American quantum century, a revolution that hums with a distinctly American frequency.